this is chapter 8. What's interesting is like I feel like chapter 7 and well even 6 were the start of a lot of the stuff we use more often in real life stuff, and everything else before that was kind of foundational concepts, I guess. And so as we try to figure out how much time you spend on the foundational and then how much time you spend on the stuff you would actually use, you don't always use it in this form with all these formulas, but the concepts, I guess, you do. So chapter 8 is about confidence intervals. This has to do with us knowing, so we've kind of moved into this world of inferential statistics where we take a sample and we try to make inferences about a population from the sample, okay? And so when we do that, we need to know how good we're feeling about those inferences, how confident we are that those inferred statistics are roughly close to the actual population. So anyway, you can see the little chapter map. It breaks it down. And let's just talk about it. So it starts with what's called a point estimate. This is something we've been doing all along. Okay, it's a single value that best describes a population of interest. The sample mean is a point estimate of the unknown population mean, right? So if we're talking about, if we have a data set that says, how many hours of TV does the average American watch per week, and we come up with some crazy number. That one thing we were looking at was like 4 hours a day or something like that. So let's say we come up with a sample mean of 20 hours a week people spend watching TV. That is what's called a point estimate for the population, right? And of course it's going to vary. There'll be people who watch more than that and people that watch a lot less than that, down to people who watch nothing. People can't watch, if you think about it, 0 is the lowest it could go, but it could go, and there's an upper limit, which would be 24 hours times 7 days a week would be the most somebody could watch in a week if they just left their television running the whole time or something like that. So a point estimate is a single value that best describes the population of interest. And so we'll use a sample mean to estimate the unknown population mean, or a sample proportion, right? Some proportion of the sample, 30% do this or whatever, to estimate an unknown population proportion. They're easy to calculate, but as with most things in life, the easier it is, the less accurate it is and the less valuable, okay? So they don't provide any information about their accuracy. So what we're going to learn about in this chapter is creating an interval estimate that provides additional information about the variability of the data set. Or in other words, if we can say, like, here's our sample mean, and we think it roughly matches the population mean, but even better is here's a range that we think that we have about 90% confident is going to contain the population mean. Okay, that's what confidence intervals are all about. All right, so this chapter about confidence intervals is broken down into 3. It's got more than 3 sections, but the part about confidence intervals is broken into 3 subsections. The first is when we're dealing with a population mean. In other words, we're going to make an assumption about the population average or mean from the sample mean when we know the standard deviation or when we don't know the standard deviation. So many of these problems, they tell you, you're supposed to find this information from this sample when the population standard deviation is this. And you're thinking, if the population is roughly infinite, like the number of people in the United States, 350 million is roughly infinite for most purposes, okay? Then how are you can't really know the standard deviation of that. You can estimate it the same ways we've been learning based on a sample, but you can't know it. So even though we do a lot of problems where the standard deviation of the population is known, in real life, most of them kind of fall into this category, where you don't know the standard deviation of the population. Because you don't know the mean. That's why you're estimating it in the first place, okay? And then the third, or section 8.4, is for a confidence interval for a population proportion. All right. So the confidence interval for the mean is an interval estimate around a sample mean that provides us with a range in which the true population mean is expected to lie. Or in other words, again, if we're going to guess from our sample mean what the population mean is, we're probably going to be wrong almost every time. But if we come up with an interval, a range between this point and this point, we are relatively sure the population mean will fall somewhere in there. We have a much better chance of being right. Okay? The confidence level is defined as the probability that the interval estimate will include the population parameter of interest. In other words, the confidence level tells us how likely it is that, in the case of the mean, that the population mean will fall within the interval that we've designated. Okay? All right, so here's how we figure out the confidence interval of a mean when we know the population standard deviation. So our assumptions are that the sample size is at least 30. Why? Because we have to use a normal curve for this to work. And the population standard deviation is known. If you recall from last chapter, there's the formula for the standard error of the mean, which is the population standard deviation divided by the square root of the sample size. Okay, we just did a bunch of those problems. All right, here's why you'd want to know. So it's going to help us provide an estimate of the value of the population mean. Confidence interval is going to have an upper confidence limit and a lower confidence limit. And they're going to be spaced on either side of that sample mean. Okay, so we're going to find a sample mean and we're going to add some amount to it, subtract some amount from it, and that's going to give us the confidence interval. Okay, the limits describe the range in which we have some degree of confidence that the actual population mean lies or falls within there. Formula for the confidence interval of the mean. So for the upper confidence limit, it's the sample mean plus what's called the critical z-score, which I'll tell you about in a minute, plus the standard error, times the standard error of the mean. For the lower confidence limit, it's the sample mean minus the critical z-score times the standard error of the mean. Okay? What's cool about these critical z-scores, the name sounds all scary, is once you know them, you don't have to find them each time. In other words, kind of like when we were doing those ones last chapter and it was like 95%, what were they? And the z was 1.96. For 95% probability. Well, these work the same way. Because you're working in z-scores, they become constants, right? A z-score is shown in standard deviations. And so we know, for example, that a z-score that encompasses whatever it was, 95% or whatever, was a 1.96 z-score, okay? So once we know these, it's just a matter of plugging in that number and actually give you a little chart in the book that shows you the critical z's for the most common. Usually confidence intervals they're looking for is either an 80%, a 90%, a 95, or a 99. And so those z's are just kind of available to you. All right. So z alpha divided by 2 is called the critical z-score. The variable alpha is known as the significance level. Okay? Just so you know, the significance level is always the complement of the confidence level. So if we're looking for a 90% confidence level, then our significance level is 0.1. Okay, and that'll make more sense as we go forward. So here's an example. If alpha equals 10, then z alpha divided by 2 is z to the 0.05, and that equals 1.645. And again, that's like a constant. So anytime we're looking for a situation with a significance level of 10%, meaning a confidence level of 90%, the z is going to be 1.645. The reason it's divided by 2 is because if 90% falls in here, then 5% is going to fall above that 90% mark, and 5% is going to fall below. Right? 10% falls outside of it, or outside of this area, 5% above and 5% below. That's what's so wonderful about using the normal curve for all these things is they're symmetrical, right? And so you can start to make some pretty easy assumptions. So the total area to the left of the right-hand boundary is 95%. The 90% that's in the middle plus the 5% that's outside of the confidence interval. The total area to the left of the left-hand boundary is 5%. All right? All right, an airline wants to estimate the number of tickets sold for a daily flight between Dallas and Denver. Suppose a sample of 35 flights gives a sample mean of 145.5. Assume that the standard deviation of the population is 30.2. In this scenario, we really could know the standard deviation of the population, right? Calculate a 90% confidence interval for the population mean. So the first step is to find the standard error of the mean, which is to take the population standard deviation divided by the square root of n, or the number in the sample. That gives us our standard error of 5.105. Now we find our z, our critical z, okay, which is 1.645 for a 90% confidence interval. And then we calculate the interval endpoints. Remember, we take our mean of the sample and we add the critical z multiplied by the standard error. Then we do the same and subtract it. That gives us the confidence interval. So now what we're saying is, based on this information with a sample mean of 145.5, we're 90% confident. That's what this 90% confidence interval means. 90% confident that the population mean number of tickets sold is somewhere between 137.10 and 153.9. It is. It's an estimate. But in many instances, I would much rather, if I'm trying to determine whether or not something's true, having a range that says, 90% confident that it falls within this range, if it starts to fall outside of that range, I can start to say, I'm not real confident that it's there or whatever, and that's the idea behind this. All right, so the margin of error is the amount added or subtracted to the point estimate. So if you think about it, the margin of error equals this critical z times the standard error. Remember, we went back and did. So this part of it is called the margin of error. So all we're doing is taking the mean and we're adding the margin of error and subtracting the margin of error. Okay? Oh, and then you can see right there it shows you it's the critical z times the, what do we call that, the standard error. All right, so increasing the sample size while keeping the confidence level constant will reduce the margin of error. As the n goes up, the standard error goes down, which we established in Chapter 7. And as that goes down, the margin of error goes down. Makes sense, right? In other words, this range we're saying that we're 90% confident that the population mean falls into, the higher our sample size, the narrower that range will get. Until theoretically, if the sample size equaled the population, then we would know that our mean of our sample would equal the mean of our population because they'd be the same thing, right? So that's the logic there. All right. So we're 90% confident the true mean is between 137.10 and 153.9. Although the population mean may or may not be in this interval, close to 90% of a large number of sample means drawn from the population will produce confidence intervals that include the population's mean. In other words, in small numbers, it's hard to know. So when we're making these sort of inferential statistical estimates, we know that over a large number, it's going to be right. But over a small, any given number could not have something that falls into that mean, right? Or into that range. An incorrect interpretation is that there is 90% probability that this interval contains a true population mean. So we're saying we're confident that we're 90% confident that this is the case, not that there's a 90% probability. This interval either does or does not contain the true mean. There's no probability for a single interval. Instead, we're giving our confidence that over a large number of tests, if we took a large number of samples, they would fall within that range, or the mean they would fall within there. All right. The significance level, or alpha, represents the probability that any given confidence interval will not contain the true population mean. The confidence level, or 1 minus alpha, is a complement. Confidence intervals get wider if the confidence level increases. That's not that important. It'll all make sense as you do it. All right, consider a 95% confidence interval. So now, the shaded area is 95% of the total area, and there's 2.5% on either side. Okay? We would say that the confidence level of that is 0.95, and the significance level is 0.05. They're always a complement to each other. Confidence level of 95% is a critical Z of 1.96. Again, that's in your book as well.
The confidence for the critical Z score always stays the
Mm-hmm.
same.
Because it's in standard deviations. Okay, and so, in other words, to say the Z score, if I want an interval that includes 95% of all of the possible data points in this curve, then I need to be plus or minus 1.96 standard deviations from the mean.
So they're going to be, so for this 8.1, are we specifically working with things that we know as far as the scores?
Uh-huh.
Find it, just like it next.
What do you mean by things that we know?
Well, the critical Z score, we know that.
Right.
Are we going to be given?
So the only time these won't work is if we're working on something that's in a non-normal distribution. Okay, and so actually at 8.3, when we're working with proportions rather than the actual data points, so when they say 30% of the population or 30% of the sample conform to this, remember when we're working in proportions, now we've switched into a binomial situation. It either is or it isn't. But as long as our n is big enough, we can use the binomial, we can use the normal curve still to approximate it, and they'll talk about that a little bit. All right. Hey!
Yes.
Excel has a function called confidence.norm. The confidence.norm function has the following characteristics. Confidence.norm, alpha, comma, standard deviation, comma, size, where the alpha is the significance level. So again, if you're looking for a 90% confidence level, that means your significance level would be 10%. Okay? The standard deviation is the standard deviation of the population, so that works for these where we know the standard deviation of the population, and size is your n, or sample size. When the sample size is less than 30 and sigma is known, sigma again is the population standard deviation, the population must be normally distributed to calculate a confidence interval. With n is less than 30, the central limit theorem can no longer be applied. Remember, that's what we learned about in Chapter 7. That whole reason all this works is because things conform to the curve, and they tend toward the central limit theorem. So we can't say the sampling distribution is approximately normal, but sampling distribution is always normal, regardless of sample size, if the population is normally distributed. So, all that being said, even with small samples, we're going to use the same process. Okay? Here's an example. A manager wants to know the average time it takes to complete the required forms to hire a new worker. Suppose the sample size of n equals 18 gives a sample mean of 1.28 hours. Assume that we have a population standard deviation of 0.2 hours, and the population follows the normal distribution. Calculate a 95% confidence interval for the population mean. So first thing we do is find the standard error by taking the population standard deviation divided by the square root of the sample size. That gives us 0.047. Find the critical Z for 95%, which we know is 1.96. And then we calculate the interval points. 1.28 plus that, 1.28 minus that. That gives us a range that our sample mean, 1.28, we have 95% confidence. The population mean falls between the lower limit and the upper limit. Okay? This isn't too hard, actually. I think the hardest thing in statistics is like just as you look at all the names and you look at all the thetas and the alphas and it's easy to like let that get in your head and be like, oh, this is crazy math. But when you get down to it, you take the mean and you add some amount and subtract some amount, And you can calculate that amount simply by finding the standard error and multiplying it by the critical z. Or better yet, you can plug it into Excel and it will give that to you. But even if you didn't have Excel, that's easier than some stuff we've done already. Okay. All right. So now we're in 8.3, calculating confidence intervals for the mean when the standard deviation of the population is unknown. This is more real life stuff. You don't usually know. If we're talking about all the shoppers in America and how much money they spend, any estimate of a standard deviation or the mean of that population is just going to be an estimate. So what do we do about it? So when the population standard deviation is unknown, we substitute S, the sample standard deviation, in its place. I like in the textbook, he says, if that sounds too easy to you, you're probably right. Because again, this assumption that the standard deviation of the sample is going to somehow be representative of the standard deviation of the population is a big assumption. It's a big leap to make. Okay? So here they give you the formula for the standard deviation. This is stuff we learned all the way back in chapter 3. So now we have to use a different distribution. Because we're having to use this, because we're estimating, I guess, the population standard deviation using the sample standard deviation, we're going to use what's called a t-distribution. Sometimes it's called the student's t-distribution, but they usually just refer to it as a t-distribution. It's used in place of normal probability distribution when the sample standard deviation is used in place of the population standard deviation. Okay? So when we don't know the population standard deviation, we use the sample standard deviation, and now we're going to say this follows a slightly different curve, the t-curve, or the t-distribution. It's a continuous probability distribution with the following properties. It's bell-shaped and symmetrical around the mean. Sounds a lot like a normal distribution, right? The shape of the curve depends on the degrees of freedom. If you're interested, the book gives a fairly long treatise on what degrees of freedom mean. Mostly, all you need to know is that degrees of freedom is n minus 1. Okay, but if you're interested, he goes into this lengthy explanation, and you're like, gotcha, n minus 1. All right. So n being the number in the sample. Okay. The area under the curve is equal to 1, so that's like a normal distribution. The t-distribution is flatter and wider than a normal distribution. And the critical score for the t-distribution is greater than the critical z-score, so they'll call it a critical t of the same confidence level. What this means is, in essence, if you don't know the population standard deviation, your confidence interval is going to have to be wider. To say we're 90% sure that the true population mean falls within there, we're just going to have a bigger range to say we're 90% sure. The t-distribution is actually, it says, a family of distributions. As the number of degrees of freedom increases, the shape of the t-distribution becomes similar to the normal distribution. With more than 100 degrees of freedom, a sample size of more than 100, the two distributions are practically identical. Okay? So there's an example. There's our normal distribution in green. Then you can see a t-distribution. In red there is when you have 5 degrees of freedom. Remember, that's n minus 1. That would mean 6 in the sample. And then with 13 degrees of freedom, you can already see in the black how much of a change that makes. And if we get up to 100 degrees of freedom, meaning a sample size of 100 or more, it pretty much approximates a normal distribution. Comparing t-scores and z-scores. That'll give you an example. So in other words, to be confident that something falls within a 95% confidence level, with our z, meaning using a normal distribution, we have to be plus or minus 1.96 standard deviations from the mean. But if we have only 10 degrees of freedom, we've got to be plus or minus 2.228 standard deviations from the mean. So it's just got to be a wider range. It's kind of like you have to cast a broader net because you're less confident because you don't know the population standard deviation. That's all that this really means. Well, no, it's more like saying, you know, if I knew the standard deviation of the population and I could use the normal distribution, I would know, or at least be 90% or 95 or whatever percent confident that the population mean falls within this range. But if I don't know the population standard deviation, I have to use a t-distribution. And depending on the sample size, I'm going to have to really widen that range to still say I'm 95% confident it's there. So it's still an educated guess. It's just that now I'm saying in order to feel confident in this, I'm going to give you a much larger range and say I'm pretty sure it falls between 5 and 50 or whatever. The example he gives in the beginning of the book is really interesting. It's on, you know, the numbers that the Bureau of Labor Statistics always puts out on unemployment levels? Well, so they'll put out this number that says, you know, hey, unemployment fell from 7.6% to 7.4% in the last quarter. And they'll really be like, yay, you know, things are getting better. And then if you look at their confidence interval, it could actually be that, I mean, it's a wide enough range to say they're 90% or 95% confident that unemployment could have actually gone up, or it could have gone down more than that, right? They're reporting the mean of their data set, but their confidence interval shows that they're not perfectly sure. To say they're 90% sure, there's got to be a range of means that it could actually be. All right. Formula for the confidence interval for the mean, it's exactly the same as with the normal distribution, except we're using a critical t-score instead of a critical z-score. Okay? Here's an example. A hospital manager wants to estimate the average number of days patients spend in the hospital for surgical procedure. Suppose a sample of size n equals 15, has a sample mean of 5.11, a sample standard deviation of 0.85. Calculate a 95% confidence interval. So first, find the standard error, which we find. Second, find the critical t. You can look it up in Appendix A, Table 5, if you want to. And you'll get the 2.145, and then you just calculate it out. 5.11 plus the critical t times the standard error. 5.11 minus the critical t times the standard error. Or you can use this function in Excel. The critical t-score can be found with Excel's t.inv.2t. I don't know why that's what the function is, where you have to do the alpha and the degrees of freedom. And remember, the alpha is the significance level or the confidence level. And degrees of freedom is n minus 1. Of the confidence level. Just remember, significance level is the confidence level. 1 minus the confidence level. So if you're looking for 90% confidence interval, then your significance level is 10%. Okay, that's the thing that, like, I always would forget. I guess that's why I keep repeating it, because when I was learning this, I was always like, what is a significance level? Like, what does that mean? Well, it's not that hard. Also, the Excel function confidence.t provides the margin of error for a confidence interval for the mean when the population standard deviation is unknown. Where alpha is the significance level, standard deviation is the standard deviation of the sample, and size is the sample size. There you go. All right. Finally, we have calculating confidence interval. Not finally, there's actually 2 more things after this, so don't get your hopes up. But this is the last, talking about confidence intervals. So calculating the confidence interval for a proportion. Proportion data follow a binomial distribution, which can be approximated by the normal distribution under the following conditions, where NP is greater than or equals to 5, so the sample size times the probability of success in the population, if that's greater than 5, and n times 1 minus p is greater than or equal to 5. If those 2 conditions are met, we can assume that that binomial distribution follows, or it can be approximated by a normal distribution. All right, the confidence interval for the proportion is an interval estimate around the sample proportion that provides us with a range of where the true population proportion lies. So the formula for the sample proportion is the number of observations of interest divided by the sample size. In other words, if 3 out of 10 in the sample were a success, then we would say that the population proportion is 0.3, right, or 30% of it. The formula for the standard error of the proportion, again, this is stuff we did last chapter, okay, is the proportion times 1 minus proportion over n, and you take the square root of the whole thing. Since the population proportion P is unknown, It's estimated using the sample proportion. So there's the formula for the approximate standard error of the proportion. Again, we did this last chapter. Take the sample proportion times 1 minus the sample proportion over n, take the square root of it. Formula for the confidence interval for the proportion is the sample proportion plus the critical z-score times the approximate standard error of the proportion. So they're very similar to the ones we just learned, okay? Formula for the margin of error for a confidence interval of the proportion. Same thing. Remember, the margin of error is just that part of it. The critical z times the standard error. So that's what the margin of error is. Here's an example from a random sample of U.S. citizens. 22 out of 100 people are found to have blue eyes. Calculate a 98% confidence interval for the population proportion of blue eyes U.S. citizens. Step 1, calculate the sample proportion and the approximate standard error. Step 2, find the critical z. 3, calculate the interval endpoints. And then you have your answer. We're 98% confident the population proportion is between 0.124 and 0.316. That's a pretty wide range, right? We're 98% confident that out of all the people in the United States, that between 12.4 and 31.6% of them have blue eyes. That's a pretty huge range. If you put that into absolute numbers, right? 12% of the U.S. population would be what? 3.7 million. 30% of the U.S. population would be 100 million. So somewhere, think about what they're saying. Somewhere between 36 and 100 million people have blue eyes. That tells me not a whole lot, right? I'm 98% confident of that. Depends on where you got your sample from too, right? Would you guess Arizona with a higher Hispanic population would have a lower percentage of people with blue eyes? Probably, right? Anyway, so you got to be careful when you sample. Well, we already learned that lesson. All right. Sometimes we need to determine the sample size we need in order to have the confidence interval we're looking for. So in other words, you'll say, hey, I want to have a confidence interval of 98%. I want to be 98% confident that my population mean lies within these parameters. So the question might be, how big of a sample do I need in order to have a 98% confidence interval? So this is kind of like turning the whole formula backward to calculate for n. By the way, there's calculators online that do this, because when you have to do research and you're not a research expert or a statistics expert, you just want to punch in, here's the population size, and here's the confidence interval I'm looking for. What's the sample size I need? Okay, but we'll show you how to do it. So the sample size needed to achieve a specific margin of error can be calculated given the following information: the confidence level and the population standard deviation. So all you're doing is solving for n. They show you all the math there to do it. Really all it is the critical z squared times the population standard deviation squared over the margin of error squared. So if we have a population standard deviation of 45, what sample size is needed to be 90% confident of estimating the population mean with a margin of error of 0 plus or minus 5? So we find our margin of error for 90%, 1.645. We calculate the required sample size, 1.645 squared over 45 squared divided by 5 squared. Boom. So it's not too bad, all right? Plug and chug. Excel does not have a function for this. PHStat does, kind of, but we're not paying for PHStat, all right? You can if you want to. Let's see, calculating the sample size to estimate the population mean. So the population standard deviation might not be known. If not, we'll have to estimate again with the sample standard deviation. So if you look at that, it looks way different. It's actually the same stuff. All right. In order to calculate the required sample size to estimate P, the population proportion, we need to know bar P of the sample, or the sample proportion. Select the pilot sample to use the sample proportion. If it's not possible to select a pilot sample, then you set it to 0.5. The reason is, setting it equal to 0.5 provides the most conservative estimate for a sample size, right? We're taking, since it falls between 0 and 1, we take the middle, and that gives us the best samples, the best estimate. So here's their example. What sample size needed to estimate with 95% confidence the population proportion of U.S. citizens with blue eyes within a margin of error of plus or minus 5%. Assume a pilot sample of 100 people found 22 with blue eyes. Again, take our critical Z, square it. We take our proportion, 0.22, times 1 minus 0.022. So you're always taking the proportion multiplied by the complement of the proportion. You've seen that in almost everything we've done with proportions. And then we divide that by the margin of error squared. That comes up with 263.9. It tells you when you're doing these to always round up for sample size. So don't round it off, round up to the next whole number. Because in real life, you're talking about people, right? And so we just always say, take one more person. The reason is if we need to know what sample size we need to do this, we'd rather have one extra person than one too few to get us that confidence interval. All right, finally, calculating confidence intervals for finite populations. Remember we learned about our finite population correction factor back in chapter 7. And remember we defined a finite population as one in which n, the sample size, divided by big N, the population size, is greater than 0.05. So if our sample is more than 5% of the total population, then we're saying we need to use this correction factor. And it's the square root of the population minus the sample size over the population minus 1. So that's not an issue when we're talking about things like they have nearly infinite populations. Like if our population is all the United States or all the people in the world or the number of sands in the sea, right, then this doesn't really apply. But when our population only has 100 things in it, my question is always like, if your population only has 100 things in it, then why not? Then why even use inferential statistics? Just ask all 100 people. But that's not always possible. So the formula is the exact same as the formula from earlier in the chapter, multiplied by the finite population correction factor. That's all. Same thing. So this is where we know the population standard deviation. Here's where we don't know it. So the only difference you'll see is the Z, critical Z or the critical T, right? Factor is the same. And for proportion, again, exact same. Only difference is this little factor. One last example. Number of steps per day was measured from a sample of 100 students from a college's student population of 1,600 business students. Sample mean was found to be 5,530 steps per day. The sample standard deviation was 1,480 steps per day, calculated 95% confidence interval. So the first thing I'm going to do is find the finite. So the first thing to do is find out whether or not this is a finite population, right? So they take the number in the sample divided by the number in the population and find out that it's greater than 5% of the population. So next they say we need to do the correction factor. So we take 1,600, which is the population size minus the sample size divided by 1,600 minus 1, take the square root of that, and we find out that our correction factor is 0.9686. Next, we calculate the approximate standard error. Then we find the critical T. Wait a minute. I thought they told us the population standard deviation, did they not? I guess they didn't. All right, so we have to find the T. Then we multiply it all out. Piece of cake. If we want, we can interpret the results, which just means we restate them like that. They're 95% confident the average number of steps per day taken by the population of students is between this amount and this amount. And that's it. Piece of cake. I think you guys will do this one pretty easy.